Hello and welcome. In this video, we are required to find the current flowing through the variable resistor when the resistance is 0 ohms, 5 ohms, 40 ohms, and 95 ohms. We are going to be doing this using Thevenin's theorem, and the first thing we want to do when we use Thevenin's theorem is we want to detach the resistor that we are curious about. When we detach it, it will create a two-port network. And that will look something like this, with two ports A and B that we can use to signify our two-port network. And the next thing we want to do is that we want to estimate the current in different parts of the circuit. And doing that, we can simply use our nodal analysis. We have one node here. We have another node here. So let's call that node 1. All this is one node. Then we have another node here. Let's call that node 2. Then we can write node equations at each node. Now at node 1, we can write the KCL equation there. We have the V1 divided by 15 minus 5 amperes plus V1 divided by 10 plus V1 minus V2 divided by 4. V2 divided by 4, and that is all equal to 0. That is KCL equation at node 1. Then at node 2, we can write another KCL equation, and that would be at node 2. We have it that V2 minus V1 divided by 4 plus V2 minus 126 divided by 6 plus V2 minus 126 divided by 6. Okay, I think that's all we have at that node. All equals 0. We can then multiply this through by 12, and we'd have 3V2 minus 3V1 plus 2V2 minus, and that would be 2, 4, 5, 2, 5, 2, 2, 5, 2 equals 0, and that would further simplify to be 5V2 minus 3V1 equals 252. And call this equation 2. Just remember that we didn't simplify this one, so we can simply multiply through by 60. If we multiply through by 60, we would have 4V1 here. 60 times 5, 300, minus 300 plus 6V1 plus 15V1 minus 15V2 equals 0. And if we simplify this further, we would have V1, that would be 25V1, okay, minus 15V2 equals 300. I'll call that our third equation. We can solve equation 3 and equation 2 simultaneously, and we'll derive at the values of V1 and V2. And with this, V1 would be equals to 66 volts, and V2 would be equals to 90 volts. So we know that the current flowing in this branch would be V2 minus 126 divided by 6. And V2 minus 126 divided by 6 would be equals to minus 6 amperes. So we have a current that is flowing in this direction, and it is 6 amperes. So the next thing I want to do to calculate the value of VTH is we want to connect a voltage source across this port, and that will be the value of VTH. Then we'll write a KVL equation. Yeah. Now we know that no current is flowing in this resistor, but we know that we have 6 amperes flowing in this branch. So we can write a KVL equation in this branch, and we would have it that 126 minus 6 multiplied by 6, this is 0, minus VTH equals 0. And with that, we know that VTH is equals to 90 volts. So now we have the value of VTH. The next thing to do is to calculate the value of RTH. Now, calculating the value of RTH requires us to open circuit the current source and short circuit the voltage sources. Then from there we can calculate the equivalent resistance of the circuit. And with that, we have a circuit that looks something like this, where the current source is open circuited and the voltage source is short circuited. And RTH would be what you would measure with an ohmmeter across these terminals. And with that, RTH would be equals to, without these two in series, this 15 ohm and 10 ohm. So sorry, we have them in parallel. So we have 15 in parallel with 10. Then we have these two in series with this 4 ohm. 4. Then all of that would be in parallel with this 6 ohm. Okay. Then that would be in parallel with this 1.25 ohms plus 1.25. Now, this will simply be 15 times 10 divided by 15 plus 10. That will be 150 divided by 25, which would be equals to 6 plus 4 in parallel with 6, which is all in series with 1.25. Now this would be 10. This would be 10 in parallel with 6. Now that would be 10 times 6 divided by 10 plus 6. So 10 in parallel with 6 all plus 1.25. And with that, we would arrive at 3.75 plus 1.25. Then we add them together and we would have 5 ohms. And we have it that the value of RTH is 5 ohms. We can then go ahead to construct our Thevenin equivalent circuit, which would look something like this, where VTH is 90 volts and RTH is 5 ohms. We can then go ahead and connect our variable resistor across the terminals A and B. Across the terminals A and B, and this would be the R0, which will vary. Now, when the resistance is 0 ohms, the total resistance in the circuit will be 5 ohms. So the current I0 flowing through the resistance would be 90 divided by 5, and that would be around 18 amperes. We should state explicitly that I0 is equals to 90 volts divided by 5 plus R0. And so when I naught is equals to 5 ohms, I naught would be equals to 9 amperes. And when I naught is equals to 40 ohms, we expect I naught to be equals to 2 amperes. And when I naught is equals to 95 ohms, it is expected that I naught is equals to 0.9 amperes. And that will be all for today. Thank you for watching. Don't forget to hit the like button and subscribe. See you later. Bye.